Let's start. So this afternoon we have two talks. So the first one is by an early career. So Maciej is a postdoctoral researcher at Heriot-Watt University.
Thank you, Angela. Hi, everyone. So thanks a lot for giving me the opportunity to speak here and to attend this program. It's my first time at Newton Institute. It's been very satisfying and gratifying 2 weeks, and I still have this week to look forward to. And as Angela mentioned, at the moment I'm a postdoctoral researcher at Heriot-Watt University. Prior to that, I was a postdoc with Angela at Cardiff. That was my first postdoc, which coincided with the pandemic. And part of the work presented today was done in collaboration with Angela and Thomas from Cardiff as well. And we are trying now to take it further with Geneviève Toussaint, who I met at Warwick, where I did my PhD. She was a postdoc there. Krista Portner was my PhD advisor. He was at Warwick, now he's at UBC in Vancouver in Canada. James Kermode is a professor in the School of Engineering at Warwick, and he's the director of the Warwick Center for Predictive Modeling, and they do a lot of atomistic modeling, and Ian is his PhD student. Right. So I thought, since I mentioned interatomic potentials, it's the atomistic modeling of materials. So it's multi-scale modeling, really. And typically when people present work on this topic, they start with a slide like that, which essentially shows you the different length scales and time scales in multi-scale modeling. So at the smallest scales, both in length and in time, you have quantum mechanics, where not only do you model the nuclei of atoms, but also the clouds of electrons around the nuclei. And then as you want to access further timescales and length scales, you need to coarse grain. And one way of coarse graining is to jump from quantum mechanics to interatomic potentials. And the idea is that you drop the modeling of electrons, and you end up with a discrete model where atoms are just points that interact in a very nonlinear way that is meant to resemble the quantum mechanical effects. If you want to go even further, at some point, you still have to model billions of atoms, and they attain all sorts of structures. Sometimes you're only interested in the structure itself, as opposed to what every atom is doing. Then you can coarse grain again, and for instance, we see the jump from here to here. These lines are dislocation lines, and this simulation is called discrete dislocation dynamics. And you basically just trace the fronts of these crystalline defects, and somehow you disregard the information about atoms. You can also jump further to polycrystalline materials. So then you have crystalline structure with different orientation, and then at the boundaries, you typically have an awful lot of these dislocations that try to correct for the misalignment of atoms. And then you can coarse grain even further, and ultimately you reach the sort of macro scale, the finite element scale, the continuum scale, where, for instance, you do homogenization at this stage to get some effective material properties that you can then pass on to finite element simulations. And here we also see some of the sort of experimental techniques that can be used to sort of track these different length scales and time scales. And so my work to start with was here. It was the applied analysis, as we call it in maths. So we take problems of crystalline defects in an idealized setting, and we prove regularity, for instance. So if you have some defect like fracture or dislocation, you prove the properties of equilibrium configurations. You can also do numerical analysis, which is that you ideally would like to model it for billions of atoms. That's not feasible. So if you constrain yourself to a smaller box, what kind of error you make. So it's a bit like with finite element mesh, like what's the error compared to the true PDE solution. Then when I moved to Cardiff, since Angela is an expert in continuum stochastic elasticity, we were thinking that, I should also mention that between all these models, you can also jump, for instance, directly from the atomistic to continuum, at least in idealized examples. And so the idea was to, since there's a lot of stochastic elasticity literature, and there is a way of connecting these two scales directly, the question was, can we use these ideas to translate them back to the atomistic scale? And at the moment, the extension of this, or other aspects of it, is about fitting machine learning interatomic potentials, which are the sort of modern version of empirical interatomic potentials. We fit it with machine learning techniques to quantum mechanical data. And the idea is that you are able to reproduce an awful lot of quantum mechanical effects to the point where it's almost as accurate as quantum mechanics, at least in principle. And again, we'd like to focus on the idea of trying to understand the uncertainty quantification when you go from quantum mechanics to interatomic potentials. And separately, I'm currently at Heriot-Watt. We are doing this scale here. We do geometric models of polycrystals. So essentially, you have this electron backscatter diffraction measurements, which tell you if you have, for instance, steel, what are the grains, what are the orientations, and we use optimal transportation theory to very quickly be able to generate artificial microstructure that resembles the real one as much as possible, so that if you can generate an ensemble of artificial microstructures, then you can quickly do homogenization and you have you can pass it on to higher scale. Okay. So the outline of the talk here is, I've already sort of mentioned it. So first of all, I mentioned the work with Angela, and the general question here is, like, given a crystalline system of atoms which you model with an interatomic potential, is there a way to form meaningful priors for the potential parameters based on physical constraints, prior distributions? We're talking about the stochastic modeling of these things. And then the second part, it's the current work that I'm trying to push forward here while visiting Newton, is how to reduce parametric uncertainty when we derive machine learning potentials from quantum mechanics data. Okay, so part one is the work that's already been done, and the motivation is, again, it's the same question as on the previous slide. And as I alluded to already, the idea is that there's a lot of sophisticated literature by now about continuum stochastic elasticity. Angela has recently published a book on the topic. And in the tutorial week, 2 weeks ago, we had a series of lectures by Christian Suaz precisely on this topic. So some of the lectures were related to using information theoretic framework to derive least bias prior distributions for model parameters at the continuum level. And the idea is that if you have an atomistic model, you can link it to continuum by what is called Cauchy-Born rule. And we explored how these two can be combined to say something about the question at the top. Yeah. So let me try to introduce the setup. So we are interested in a system of M atoms, and they are in a crystalline body, and they occupy positions capital R. So if I try to draw it, let's say we are in 2D, to make it simple, and let's say that we have a square lattice, which is not really physical, but it's simpler to draw. So the idea is that we have some atoms. Typically, we supply some periodic boundary conditions or some other boundary conditions that effectively we just model atoms in a box, and we can label them. So they will be from 1 to M, and we introduce an energy that depends on interatomic potential. And the idea is that you express it as a sum of body order expansion. So I'll untangle this formula on the next slide, but essentially the point is that you first look at two body terms. So you compare the interaction between these two atoms, for instance, separately, then between these two atoms, then between these two atoms. And that's all the two body terms you iterate between all the pairs. Then if you go to three body terms, you basically have like a central atom, and then you look at the triplets. And for instance, in this case, you perhaps are interested in the distance between the central atom and the two other atoms and the angle that the three atoms create together. And then you can go beyond to nth body order in such a way. Typically, the one body term is related to external forces. So for the sake of presentation, we disregard it. And in our work, in our work with Angela, we just looked at the model case of a Lennard-Jones potential. Later on, we also looked at the prototype machine learning potential, and I'll mention that at the end of this part. With this formulation, what you can do to make it look like a bit more like continuum elasticity, you might want to rewrite it as a sum of site potentials. So you first iterate over all atoms, and then once you have your central atom, you're interested in the interactions with its neighbors, nearest neighbors, second nearest neighbors, and there's some interaction radius. So it's non-local interactions. And for instance, the underlying assumption is that first of all, if we rotate the whole system, nothing changes. If we translate the system, nothing changes. And if we exchange two atoms, nothing changes because they are the same atoms. And if you try to encode that functionally, that means that, for instance, for two body terms, all that enters is the distance between the two atoms. And at three body terms, all that enters is either just the distance between the triplets of atoms or the distance between some central atom and tuple, where the distance to these two atoms and then the angle between them. But to make it easier, I just use the distance between the three. And we are interested in crystalline materials, so we will have a reference configuration, which is a Bravais lattice. So here is the square lattice, but you can also have a triangle lattice in 2D. And so the idea is that the configuration of atoms is there's some reference configuration, which is the lattice, and then we look at the displacements from the lattice. And so in the language of continuum elasticity, if you look at deformations, so there'll be a deformation which deforms the lattice according to some displacement u. You end up having so your mth atom, which you can label, and then it's the jth atom, is its original configuration, and then some displacement, and then these distances between atoms, they can be encoded as finite differences and discrete gradients, as opposed to derivatives and continuum gradients. And then you can rewrite this energy as something that looks a bit like continuum stored energy density function. And this is the sort of the discrete energy that you work with. And I will connect to a continuum in a second, but essentially, when you try to model it stochastically, you do have some physical constraints on the system that you try to model. And one way of encoding is to say, okay, formally, I assemble this discrete energy. I have this reference configuration of a crystalline lattice that I know my material has as a ground state. I pile or expand around it to second order. I can do the calculations for any interatomic potentials, no matter how many body order terms you include. It will be written as follows, where you have all these sort of the finite differences between different atoms and different neighbors. And the typical assumption is that your potential that you use to model this material has to admit this perfect lattice as a stable equilibrium. And that means in this discrete language that first of all the perfect lattice is an equilibrium, and then that if this condition is satisfied, then this is called the lattice stability assumption. And bear in mind that since V can potentially be extremely complicated, it's a very non-convex problem. So even verifying that this assumption holds is an extremely difficult problem. And really, the view we take is that these systems exist in nature. So you want to use, so it has to be a property of the potential that if the potential is meant to model a material that is known to attain this crystalline structure, then if your potential does not satisfy these conditions, then it's a wrong potential. But at the level of analysis, we just say we are given a potential that satisfies this. But if we want to do UQ, we would need to be a bit more specific, and hence we relax this, because this assumption would hold for any displacements, or at least small displacements, but of any type from perfect lattice. So what we do is we restrict this condition to uniform displacement. So you basically just take your lattice and shear it a little bit or squash it a little bit. And that can be encoded by a displacement that is just some fixed matrix F applied to each atom. So it's a linear transformation. That then means that the finite difference is actually given exactly by the now continuum gradient. And so simple calculations will tell you that actually and for this class of displacements, the equilibrium condition is given by this thing. And then the second variation is as follows. And so now under these slightly relaxed conditions, but they are, and this is a known result in the field, these are necessary. So for the atomistic stability to hold, this has to hold. Well, I mean, I suppose this is trivial because we just restrict to uniform displacements. But essentially, yes. So we want the perfect lattice of equilibrium. That essentially means that these constants Li alpha, they have to be 0, and they often determine what is the usual distance between atoms. And then for the second order condition, that's where we couple to a corresponding continuum model. So the idea here is that any interatomic potential, V, you can define a continuum strain energy density function W by the following formula. And that then means that if you expand it to second order to get the linearized elasticity tensor C, you actually end up with exactly these coefficients S, J, beta, I, alpha, which are from the in this formula from the atomistic calculation. And it's exactly this Jesus, I forgot the word. This relation that lets us use the continuum elasticity theory, which I will outline here. Essentially, we heard it all 2 weeks ago in one of the lectures by Christian, but the idea is that in the continuum elasticity, you have the strain tensor, you have the constitutive stress-strain relation, which is just the stress is the elasticity tensor times the strain tensor, and then the equilibrium configurations are just that the divergence of the stress is 0. And it's known, and Christian mentioned it quite extensively, that the result, the elasticity tensor is it has up to 21 independent entries, depending on what's the symmetry class that you consider, and it admits a decomposition like that. And these parameters, these are the parameters, and this is the basis of this space of admissible elasticity tensors. And they then invoke maximum entropy principle under a minimal set of constraints. So the set of constraints is that the mean value of the tensor is known. And then this is the condition that Christian discussed quite in an elaborate way, that you want the elasticity tensor and its inverse finite second moments. And one way of encoding all of these is that you write these constraints as expectations, where the function f encodes these constraints. And in particular, you can then use general results to tell you that the least informative prior density on the resulting parameters C, which define the elasticity tensor, have a joint probability density of this form, where these constraints F are encoded here in the exponential. And that's a general result. And then depending on the symmetry class that you consider, you get simplifications. And the key point is that you study the separability of the map that maps these coefficients to the logarithm of the determinant of the elasticity tensor, of the 6x6 elasticity matrix associated with the elasticity tensor. And in our picture, essentially, so in their picture, the key parameters are C's, but in our picture, in the atomistic picture, these C's, the entries of the elasticity tensor, they are themselves functions of the interatomic potential. So we basically want to invoke this maximum entropy principle on the same set of constraints, except now we have, this is a derived quantity, it's a quantity derived from the potential parameters. But still, the essential idea is that if you want to say more than have this general result, you should study the separability of this function, but now viewed as a function of the potential parameters. And we did this in a specific example of a Lennard-Jones potential. So this is a sort of classic prototype where you really just look at distances between atoms. It's a pair potential, so we only ever look at the pairs of atoms, and we basically say that we look at the distance between them, and we have this function to model them. And the idea is that this is the distance between two atoms. Atoms, of course, absolutely hate being very squashed, so it's very steep for small distances. Then there is some distance. Okay, I'll just draw the function. Then there is some distance and some small range where the atoms like to be, and they are happy to be at this distance from one another. And then if you pull them apart even further, at some point they're so far away that they stop feeling each other. So at this stage, essentially, the interaction is broken between atoms. And the A2 there essentially is an inverse of where this point is, and the A1 is basically telling you how deep the valley is. And it's a very simple potential. We just have two parameters. We can do these calculations explicitly. They simplify quite a lot. There were these LIs, which define the lattice constant. The lattice constant ends up being just a function of A2, which basically defines the preferred distance between atoms. These constants depend on, they can be explicitly calculated, depend on how many neighbors you want to include in the interaction range. And the entries of the continuum elasticity tensor that you assemble with the Cauchy-Born rule are just these. And essentially, at the end of the day, using this framework developed by Christian and Johan, we have a result like that. So if you model triangle lattice, then the maximum entropy prior on the parameters are given by the following densities, and the point is that they are actually decoupled, so they are not statistically dependent, unlike in the general result where it's a joint probability distribution. Here they decouple, and you have some hyperparameters you can play with or fit to data essentially. Yes, and we used it to do some prototype UQ for atomistic fracture because that's what I worked on in my PhD as well. So it was the was easiest to formulate it in the context of fracture. Yes, and I mentioned that we also did this for toy machine learning potential. I will in the second part, I do have. I'll get back to that. So these forms I'll explain in slightly more detail, but essentially with machine learning potentials, you want simpler functional form, not such a nonlinearity, but you want to have way more parameters. And one way to do it is to, let's say we look at polynomials with some change of coordinates, and you end up with, for instance, three-body terms that have 7 parameters. It's a cubic polynomial, and then if you try to do this framework, then you end up with a mess like that, which basically tells you that if you want to model a crystalline body and you have machine learning potential, it's very messy. All these, even under very mild constraints, you have all the parameters being statistically dependent. And it's an issue because people just say this is too complicated, so we'll assume that everything is Gaussian and there's no statistical dependency. Yes, but that's the second part of the talk, which comes now. As I mentioned, it's the idea that you start with some quantum mechanics data, you fit to your machine learning interatomic potential, and then you would like to say something about whether your fit is good or not, and whether you can sort of analyze it in mathematical terms. So these are my photos. So we are in Cambridge. Last weekend I went to Sedgwick Museum, and at the very end of it, you have a separate room about crystallography by Whewell. And I've checked that he was a polymath that shaped the mathematical tripos at Cambridge. So he was a mathematician. And the idea is that you can look at different crystalline structures there. And for instance, you basically see these crystallographic models where you have different atomic nuclei, and the quantum mechanical description of these in between these atoms, you have clouds of electrons circling around, and it's an inherently probabilistic description. And Michaela asked me how last week when we talked about it briefly, like how would you even approach this, since it is an inherently probabilistic description. And so here on just one slide, I'll try to describe it. And I highly recommend these series of lectures by Vikram Gavini from recent IPAM program, which I attended. And in basically 2-3 hours, you can get a good gist from sort of deterministic mechanics to quantum mechanics, and then approximations of it, such as density functional theory. And it's very well explained. But essentially, the idea is that in approximations to quantum mechanics, and in particular, we use the Born-Oppenheimer approximation, which tells you that because the mass of atomic nuclei are so much larger than the electrons, essentially, you can treat the nuclei position as fixed parameters, and then you simply model the electrons around it. And so if you want to have an atomistic energy of the system of m atomic nuclei at some positions, which is exact same as I described for my purely atomistic model, and then you know that for this cluster of atoms, there's n electrons around them, you end up with a nonlinear eigenvalue problem. So your energy of this configuration is a minimum over, and this is the so-called Hartree-Fock approximation. It doesn't really matter, but all I'm saying is that for a given approximation, for a given configuration of atoms, you solve an extremely complicated eigenvalue problem for wave functions and these this joint wave function and what's called the Slater determinant of these constituent wave functions of each electron separately. So you have a general multi-body wave function. You restrict it in this approximation to just looking at what's called a Slater determinant. You minimize subject to the constraint that these are normalized single electron wave functions. And then you have this Hamiltonian operator, which is as follows. So little ri's are positions of electrons, capital ri's are positions of atoms. And if you look at the Euler-Lagrange equation, you end up with a very nasty, very high-dimensional nonlinear eigenvalue problem. And there's several approaches to it, and in particular, Vikram looks at this at a different approximation, what's called density functional theory, where they use finite element methods to approximate these associated integrals. So even at that scale, you can use finite elements effectively. Yes, but essentially the point is that if you have a collection of atoms, you can do this extremely expensive calculation, and it keeps. And in the process, you also calculate the forces acting on each atom, and you can get energy and forces for a given configuration. And so the idea here in the setup essentially is that you want to study some material system, and you do these extremely expensive calculations for about a few thousand configurations that are representative of different phases of a material depending on what you model, and you do these, you collect them as energies, quantum mechanical energies, and forces as well. And then the point is that you want to fit a function that will somehow resemble the behavior of quantum mechanics in between these configurations. And here, precisely, the idea is to sort of use machine learning approaches of basically just fitting to data. And the underlying assumption in the framework that I work with is that you have this, again, this body order expansion. And these days, very popular framework is called atomic cluster expansion. The idea is that you use polynomials, so you introduce change of variables, and perhaps I can very quickly. Yeah, right. Yeah. Okay. So. Yes, so essentially, I just wanted to describe what this function ckj bkj is when we restrict to just two-body and three-body terms, and I'll just. So the general idea is that you have a k-body term, which looks at positions of k atoms, and then the sum there is basically the index ij goes from 1 to the number of atoms. So it's a nested sum where the next index sums over from 1 to n. And it's not equal to the previous index. The basic idea is that this can be represented as more like a site potential, or there is a transformation. So xk is An xk is a change of coordinates. So for instance, for two body terms, the change of coordinates is simply that because we want to respect the permutation invariance, the translation invariance, and the rotation invariance, you really only ever care about the distance between two atoms. So this ends up being a scalar function in the distances between two atoms. And then for free body terms, we have two choices essentially. And the one that I use is that we just look at the distance between all the atoms. So for two body terms, we map from so this is an this guy is R3, and so is this. We map to a scalar coordinate. Here we map to three-dimensional space, and then the basic point is that this transformations ensures that these constraints related to invariances are satisfied, and then the BK is simply higher and higher order polynomials. So B2 of X2, which is just a scalar and just the sum of and this you can choose as high as possible. And likewise, for the free body term, it's also a polynomial. It's just a polynomial in free, it's a multivariate polynomial. And the underlying idea between all these machine learning potentials, or at least a class of them, is that you go to, say, 7 body terms, you have ever more complicated coordinate transformations, and you go to ever higher polynomial degree. And so at the end of the day, when you collect all these parameters C, and you can read them off, they are here, there will be for each body order, you end up with something like 1,000 parameters that you fit to tens of thousands of quantum mechanics data. And so it's suppose it's pretty simple functional form, but the sort of the niceness of it is baked in these polynomial transform in these coordinate transformations. And surprisingly, it's known to be very accurate for giving you interatomic potentials that resemble material properties in a range of configurations. Also, you extrapolate, you go look at different configurations that you train on, and they still somehow are very accurate. And so it's, of course, a bit of a mystery why. And one of the ways to try to answer it is to perhaps try to quantify uncertainty. And a very naive way of doing it. Oh, okay. I should mention, essentially, so you gather these functional forms, you gather the training data, and then you simply use least squares. It's linear regression at the end of the day. So the point is you have your interatomic potentials, which you get from this body order expansion, where ultimately it's just polynomials. You gather your training data from quantum mechanics, and typically for this linear regression, you want to weight your energies and forces, because in some way, and it's typically done very ad hoc, and no one really knows why it works so well, but it just does. And in particular, it's linear regression because you basically just evaluate these, and it is actually linear in the coefficients. You know, all the coefficients you see, they ever enter in a linear fashion. So you can actually just rewrite it as really least squares like that. And these weights, they can be brought in as a weight matrix Q, which without any justification, but for simplicity, is just assumed to be diagonal, but you can think of different choices as well. And if you want to do UQ on this sort of already very constrained form, then one way to do it is, again, we have configurations, we have the truth from quantum mechanics, the energies, the forces. You have the model form with the coefficients entering in a linear fashion. Then you also have just the gradients of the forces. And the point is you can assume some prior distribution, and ideally you would like to use the maximum entropy framework here, but it's very difficult. So what is done in practice is Gaussians everywhere for all of it. And the idea is that you assume you have random variables, you have this error relation so that the random variable has mean described by the model properly, and then you have some random fluctuations. It's the noise vector, and it's the same Q as before, just inverted. And you essentially, so you have the likelihood given by the Gaussian with the covariance matrix Q. And then the idea is that given that you observe this quantum mechanics data, you derive a posterior distribution by the Bayes rule. And that would be like the vanilla UQ parametric approach to this problem.
Why was it too hard to do the what to do? Why did you do it?
Because if you look at, say, you constrain your polynomial degree to be 7, then these equations related to maximum entropy end up being polynomial equations in 6 degree, and the coefficients enter as coefficients in these equations, and you basically want to ensure that the solution of this equation is positive. And once you go beyond like cubic polynomials, there's no formulae, and somehow you never want to draw a set of parameters that don't give you a stable lattice. But it's the Gaussian don't. What they do in practice is they draw from it. If it doesn't work, they just give us, in the posterior they assign 0 probability. So they violate a lot of probability rules. But that's the sort of actual what happens in practice, especially for practitioners. Okay, and this is actually, at least in the Gaussian framework, it's actually connected to the least squares, because it's well known that if your prior is also a Gaussian with some covariance matrix P, and let's say this is the default set of parameters that you somehow know, then you actually end up, it's the mean of the posterior will be the minimum of what's called the regularized least squares problem. It's what's called the Tikhonov regularization, I believe. And the idea is that you basically, you nudge your least squares towards what you know about the problem. And in particular, what's extremely useful is that in here we are in the conjugate prior regime, so you don't have to do MCMC or anything. There's if your priors are Gaussians, then your posteriors will be Gaussian, and all you do is you have an update rule with related to these parameters. And our research interest here, well, one is, as I described already, that's, very simple constraints based on physics, low level, tell you that it shouldn't be Gaussian, but it just ends up being a complete mess. But then more, if you are willing to work with Gaussians, because why not at the end of the day, there are some other relevant questions. So there's an awful lot of parameters in that, these weights, Q, and the covariance here, and the prior as well. And in practice, just for convenience, they are assumed to be just diagonal matrices, but in practice, because we are in the conjugate prior regime, you can actually model these as random variables as well, and you're still in the conjugate prior regime, so you still have simple update rules. And so even including that, we think might help. But then there's another issue which Christoph recently pointed out to me, is that when they do this ACE framework, they know that when they just do deterministic fitting, they end up with something that is very accurate for, even if they extrapolate to different mechanical properties, it's very accurate. But if they try to do any sort of vanilla UQ approach, as described here, they end up with quite high error bars, and it's not representative of how accurate these things are in practice, the error bars that they get. And so the idea is that, can we look at it, like analyze it mathematically and see like how can you, in a principled way, that actually error bars can be thinner, or uncertainty bars, I should say. So really, if you want to strip away all that complexity, under the hood, these coordinate changes, they are related to spherical harmonics. And so you can think of all that fitting to quantum mechanical data as a high dimensional equivalent of polynomial approximations by Legendre polynomials, because they are the they are associated with spherical harmonics. So an absolute bare bone case, which I really like as a mathematician, is that we actually, let's go back to 1D and let's try to say, okay, let's imagine that our quantum mechanical data is a function from -1 to 1. We don't know it, and we want to model it, and this E is the representative of this interatomic potential. And we want to model it in some principled way from some partial data about the function, and in this case, it's just evaluations of this unknown function at some points in the interval, and also the derivatives, which in the full picture are the forces acting on all the atoms. And at this level of description, if you would have a deterministic model, we would say that, let's say that's our working definition, is that it's accurate if, when you train on this data and then you have some other points in the domain, in some norm, your model function and its derivative compared to the true function will be less than epsilon, which decreases with n when n is the number of data points. So the idea is that this would go to 0 when n goes to infinity. And a class of idealized functions that does this is the polynomial approximation by the Legendre polynomial up to order p, which is again somewhat reminiscent of just constraining your polynomials to some degree. But the reason why I say it's idealized is because the Legendre coefficients, they have an explicit formula, but to evaluate this formula, you need perfect information about the function you try to approximate. So it's almost like if you cannot evaluate it perfectly, it's almost like your n is already infinity because you have perfect information about the function. And then rigorous polynomial approximation theory based on, if you assume that E is of some smoothness class, then you know that these coefficients decay in some way. And so if you cut it out at some P, then you have to make some truncation error, but you can control it, and you can say that actually for any epsilon positive, this will be true. But then the question is, so, first of all, for quantum mechanics, we don't know exactly the class of smoothness. We don't know much about the function. And second of all, in here we have this idealized evaluation of these coefficients. So if you want to approximate further, so for instance, just approximate the C case, you already make some error, and then you might want to look at problem where you don't know the regularity of it, but perhaps you can infer it somehow from more data or from fitting to a higher order degree. And I can, write it all exactly in the same way as the high dimensional problem. Again, we can do it in a deterministic way. We have a least squares problem, and then that basically gives us an estimate of these idealized CKs, and then sort of this level of this abstract level of accuracy. It now is kind of an interplay between the smoothness of E and perhaps the distance of the new sets from the old set, meaning that again, making this connection to quantum mechanics, the idea is that it's such a high dimensional system that of course you don't explore the full space, but perhaps the extrapolation that they do is still on a low dimensional manifold. And so in some way, when they evaluate on some new set, it's still in some sense close to the old one, and that gives you better accuracy than you thought. But that's just on the deterministic level. On the probabilistic setting, where you can treat this as a random variable, you can do the Bayesian inference in some way, or you can do Gaussian processes, or all sorts of things. You end up with some posterior distribution, and one way you can sort of say that the model is accurate is that in expectation you have still this property that epsilon decreases with the number of data that you feed, and then perhaps also the first moment the variance decreases, but delta is again a parameter that decreases with n, and sometimes there's an interplay between epsilon and delta, and the question is like, what's the level of variance you're happy to accept? And if you're happy to accept, then perhaps you can lower the epsilon somehow. Yes, and that brings me to almost the end. Essentially, it was very fruitful few weeks being here. So especially this sort of bare bones 1D bare bones case. After listening to all the talks in the tutorial week, it was very helpful to formalize the problem, and also the discussions with Catherine the week after. And I've also looked at at least for this 1D case, it's very simple to draw parallels to Gaussian processes regression. And then if you want to go from these models to some quantities of interest, then obviously polynomial chaos expansion enters. And also I made some progress on sort of exploiting this rigorous polynomial approximation results and decay of coefficients. And the idea is to do it for these high dimensional equivalents in this body order expansion. And I also did a lot of numerical testing in Julia. And actually, since I still have a few minutes, and Catherine was curious about how Julia looks like in practice, I will just show some plots. I was meant to put them just in the presentation, but I can hopefully. So this is a Julian Notebook. It works so there's a library there called approximation of functions. It's great for any orthogonal polynomials and higher dimensional equivalents. Then there's Gaussian processes. And let's say that, our 1D function, that the unknown function is just a sine function. We also supply derivatives. Then this approximation functions library with just a simple command computes the coefficients exactly because we supply the function itself. It truncates them at the machine precision. So for this sine function, it says that actually it should be modeled with 32. So if you truncate at 32, expansion at p equal to 32, you're already at machine precision, and then you can test numerically that the decay of the coefficients is actually exponential in this case because the axis is logarithmic here. And then you can do this fitting to data as well quite quickly. And for instance, if you want to, based on 20 training points, and you want to fit a polynomial of degree 7, very easy linear regression lets you do that. You can plot it quickly. It's a nice, it's all in the Jupyter Notebook. So for instance, you see that here I don't supply the derivatives, I just supply function evaluations. And the truth is in green, and I get this is the best fit. If I do it with derivatives, which are just supplied by automatic differentiation, then I get a different fit. And the idea there is that here the fit favors being sort of aligned in terms of derivatives as opposed to just functions. And so you will get different fits depending if you supply different weights for the linear regression. Then you can do very simple Gaussian regression, which is few lines. And for instance, if you're not good with your hyperparameters, the Gaussian processes after fitting the posterior will look like this. So you have thin bars around it, which is the uncertainty, which is the variance. And you can here see that it's clearly not an accurate model. But then you can optimize them. And it's the variance up to one variant bar, I suppose. Then in Gaussian regression, of course, you have these hyperparameters that you can optimize over. And if you do that, you actually end up with an almost perfect fit, and the uncertainty is reduced almost to 0. But interestingly, if I do it live, hopefully it will work. If you supply too few points, well, that's the original bad fit. And if you now optimize over hyperparameters, what you end up seeing is actually the best way to model is to keep it flat and just increase the uncertainty. So this is almost like this interplay between the epsilon and delta, let's say. Like if you're willing to accept such variance, then at that stage you yeah, I mean, essentially the delta influences the epsilon. It's not quite, they're not at odds, but they come hand in hand, let's say. And then finally, I can do this parametric fitting in a Bayesian sense. And the idea is that, for instance, the covariance matrices that I put in, they can be taken from the Gaussian regression, or you can optimize over hyperparameters in a similar framework. And for instance, you end up with a fit like that, which the idea is, it's, again, there's a lot of parameters that you put in, but very naively, like if I increase it, then presumably the error bus will increase. And so the idea of this project and the progress I've made here a little bit is to have some principled way that tells you look at the model problem in 1D, prove some theorems perhaps about Bayesian counterpart to this modeling, and then apply it to machine learning potentials, probably without theorem proving, but show that then the uncertainty can be reduced. And with that, I thank you for your attention.
Okay, that's one quick question for Maciej, and then we will go to the next topic. Anyone has a burning question?
What you will use as criteria for the reviews of the uncertainty?
Essentially, we don't want, so one way, of course, is to supply more data and see how good the fit is. And that's obviously, if your underlying unknown function is linear, and you have 2 points, then if you put another point, then it will still be linear, right? But another way is to do a fit for larger polynomial degree. And somehow this extra coefficient that you provide are exactly 0. and that gives you more information. So our idea is to, instead of supplying more data, do a fit for much larger P and let that inform how good your original fit was. And of course, in linear problems, it's obvious, but the idea is that you will see that these higher order coefficients, for instance, are exactly 0. And that tells you that you can explain the whole thing fully, at least close to your data points, let's say.
So that can mark it again.